Okay, so it's 2 o'clock. So hello to this first lecture, which is the Introduction to Machine Learning in Python. And the first lecture today is about classifiers and linear regression. Yeah, welcome. So before I start, I just want to say a few words about the course and what you will be doing over the next 3 days. If you have any questions, feel free to type in the chat at any time. So here on this slide, I have just what I have planned for you for the next 3 days. I know not all students will be taking all 3 days. I think some of you will only be taking the first 2 days. So today, on day 1 here, we will be talking about exploratory data analysis, which is how you can look at your data before you do any modeling on it. Then I will introduce linear regression, and I will introduce a very powerful toolkit in Python called scikit-learn, which makes it very easy to make your own machine learning models. And then after today, there is also a set of exercises, which I will get back to and give you an introduction to later. And tomorrow we will be talking about, so we will take everything that we learned today and we will use it, and we will talk about molecules, and then a form of nonlinear machine learning called kernel-rich regression, which we will do in Python also. And then we will talk about how to benchmark our machine learning models also. And then the last day, oh yeah, and after the second day, there is a set of exercises. And as I write here, the second set of exercises are graded, and the deadline will be Tuesday midnight next week. And it will be using the online multiple choice quiz, just like the first set of exercises you got if you took the introductory course to Python. Then on day 3, there's a lecture, and for some reason we didn't have any exercise on that day, and so only some students will take that. And on day 3, we'll talk about neural networks and deep learning and stuff like that, and I will give an introduction to neural networks. And then I will program some neural networks with you in Python. And then we're going to do GPU deep learning. So we're going to build a feed-forward network in something called PyTorch. So definitely join day 3 if you're interested in deep learning and neural networks for sure. Okay, so let's head right into the course. So the first point I wrote up here is what is artificial intelligence and machine learning. And I'm not going to pretend that anything that we're going to program in this course is particularly intelligent. And my distinction between these two terms is that if you're doing PowerPoint slides, you call it artificial intelligence. But if you use it for your actual research, normally I just call it machine learning. So while I'm not going to make any claims about intelligence, definitely, I'm sure I can convince you that with machine learning, we can approximate some relationships. So for instance, here X becomes Y. We can approximate that using some function called here Y tilde of X. And I hope that you will all say that this sounds reasonable. And in machine learning, the way we do it is that we learn this relationship here, or this function Y tilde. We learn that by using some training data. So I'm not going to talk more about definitions. So let's just look at what we're going to do today. So the first part of the lecture is making a classifier for something called the iris data set, which I will give you an introduction to shortly. And for that, we're going to use 3 new Python frameworks, which are very handy for machine learning. It's called Pandas, and one called Seaborn and Scikit-learn. And I will demonstrate how to use that. And then the second part of the lecture is we'll do linear least squares regression for a 1D function. And then there's an exercise where you will be doing basically the same as I've been doing online in this video, or if you're watching it live. I will give you a data set for the Boston housing market pricing. And you will implement some regression models for that in NumPy and scikit-learn. Okay, so let's head into the first part, which is a dataset that is very famous in machine learning and data analysis, and it's called Fisher's iris dataset. And it's created by a biologist named Ronald Fisher in 1936. And Ronald Fisher was a statistician and biologist, and he was very obsessed with categorizing things by using statistical tools. And one of the things he looked at, which has become very famous, is this iris dataset. So he basically tried to see if he could find some rigorous way to categorize flowers by measuring various variables on them. So to the right here, I have 3 different species of the iris flower: Iris setosa, Iris versicolor, and Iris virginica. And the data set that Ronald Fisher created for this is he measured the petals and the sepals. So the sepals are the outer leaves, sort of colored leaf, and the petals are the sort of the inner ones. And for those, he calculated the width and the length. And then he tried to like use that to see if he could make some kind of classification for various species. And I think this is a very illustrative example for what we call exploratory data analysis, which is basically a way to analyze and summarize the main characteristics of a data set, like using visual methods. This is a quote from Wikipedia. And so we're going to do that. And for that, we're going to use a framework called Pandas, and we're going to use something called Seaborn for plotting. And everything is done in Python, and everything today will be done on Google Colab, just like we did in the introductory course. Yeah, so let's close the slides and head directly into Google Colab. So let's close this. Yeah, and also another thing, we made a Slack channel for this part of the course. I will paste the link in the chat right now here. There's a link directly to the Slack channel, and there's an invitation link if you didn't sign up already. Okay, so let's open Google Colab here. And I put some new IPython notebooks on my GitHub. So I will paste these links in the chat as well. They're coming here. So I believe that you have seen this a couple of times before. So the way we open these notebooks is we go to File, Open Notebook, and then because I store them on my GitHub here, you press GitHub, and then here in the field you will type my repository, which is andersx /python-intro. And here you can see all the Jupyter notebooks from the intro course, and there are also 2 new here, which are this one called Lecture 1 is the thing that I will be going through during the lecture. So and the other one is the set of exercises that you will do after this lecture. So let's open the lecture slides here. I think I'm gonna full screen this, and then I'm gonna zoom in a little bit here. Oh yeah, that should be, you should be able to see that clearly on your screen, I think. Okay, so in this exercise, I'm gonna take you all the way from a data set, which you have in a file, and to a finished classifier for these iris species of flowers. And so I made this file here. I stored it in my Dropbox, and there's a download link here. So if you want, you can like download it to your own computer, and you can watch or you can look at what is in it. So there's 151 lines, and I just printed the first 9 lines here. So you can see the data set consists of this header called petal length, petal width, sepal length, and sepal width, and which species it is. So this format is called CSV, which stands for comma separated values. And then you can see the actual values for each of these data types. So here, for example, for this flower, these are the various measurements in centimeters that Ronald Fisher did, and this is the actual classification that he gave us. Okay, so in order to download a file to your Jupyter Notebook, we use this command called wget, and you can run Linux commands. So this is built into all Linux and all MacBooks or Mac OS. I'm not sure what it's called. So if you run this line on your own Mac or Linux computer, it will download this CSV file to your computer. And because Google Colab in the background runs Linux, we can execute this cell, and it should download. Let me just run anyway. I trust myself. Cell is already running. Yeah, now something is happening. So now you can see it's doing a bunch of stuff, and here is a progress indicator, and it tells me that it saved a file called iris.csv in my Google Colab. So I told you that we will be using something called Pandas, and Pandas is a framework which reads things into something called data frames. So let's try and read this file into a data frame. And I'm going to show you some of the things that you can do with these data frames. So let's run this cell here. So what I'm doing is I'm importing pandas and then pandas. So I'm calling it PD for short, so we don't have to write pandas in full. And pandas has a function called read CSV. So we just say read the CSV file that we just downloaded, and then we store it in this data variable or object here. And then just to be sure that I read the right thing in, I'm printing here the type of the data. And you can see the type of my data frame is something called pandas core frame data frame. We just call it a data frame for short. Right now we're reading in a CSV file, but you can also read in, for example, Excel or TXT, or it has a bunch of different options. So if you have any data, chances are you can find a way to read it in via pandas. So now that we have this object called data, I can show you two very useful methods that you can use from it. And one is called data.head. So let's just try and run that. And I'm writing n equals 8. So data will print the first couple of lines from your data file. And here you can say n equals 8, so it will print the first 8 lines. And now you can see pandas actually formatted this really nicely. I can get a good overview of what's actually in the file. And you can see it actually also labeled the rows like using Python names. So it's like 0, 1, 2, 3, 4, 5, 6, 7, just like we're used to with NumPy arrays and lists. And you can see it like it grouped the petal length to the right numbers. And if we wished to do that, we could, let me just close this, we could compare these numbers to what up here, and it should be the exact same things that we see here. So another thing pandas also can do is it's very nice to give overviews of your data. And if you have a data frame, here we call our data frame data. It also has a method called, whoops, sorry about that, called describe. Let me demonstrate what that does. So now you can see here, it's giving me the same data again, or the same columns again. So it has petal length, petal width, symbol length, symbol width. And then it has how many counts of each data type. So here there's 150 entries for petal length, for instance, and you can see what the mean is, and you can see what the standard deviation of all the petal lengths are, and you can see the minimum and the maximum. And here's the 25% percentile and the 50, or normally I would call this the median. So this is like the median petal length and the 75% percentile. And this is a really powerful tool to look at your data. So often one of the biggest problems I see when people do machine learning is that you read in some data and you don't notice that there is like some kind of outlier, or some of your data was wrongly formatted or something. And so methods like this, head and describe, those are really powerful to very quickly get an overview. So for example, if our max said like 1 million here or a billion here, we would know that like there was an error somewhere, or if all these these counts weren't the same, we would know that there was something missing somewhere in our data set. So I really recommend that you read as much as possible into these pandas data frames. Okay, so the next thing is these data frames are also really useful for plotting. And for that, we can use a Python toolkit called Seaborn. So Seaborn is related to Matplotlib. So in the introductory part, we used a lot of plotting from Matplotlib and PyPlot. And Seaborn is basically a wrapper around that, which makes things very easy to generate some very advanced plots. And here I'm going to show you something called a pair plot. Let's just run this. So what I'm doing here is I import Seaborn, and I call it SNS for short. And then I import matplotlib.pyplot, and I call it PLT for short. And then this is a command to do a pair plot. And then here, this is the plot for showing something. So let's just run this, and hopefully this cell will finish. And it produces a very advanced plot. This would take a long time. Let me just zoom out a little bit so everything can fit on the screen here. Yeah. So this would take a very long time to program in Matplotlib yourself. And what we're looking at here is, so we have these 4 measurements for each of the flowers. And you can see here is like the correlation plot of how everything correlates and is distributed. So for instance, this plot down here is the petal length correlated with the sepal width. And you can see there's some correlation, and the same for the petal width and the sepal width, and the sepal length and the sepal width, and so on for each of these four properties. And on the diagonal, instead of just showing the correlation between, for instance, the sepal width with the sepal width, which would obviously just be a straight line, it's showing the distribution of the data. So this is a very good tool to get overview of your tools and finding correlations between things. Yeah, it's just really handy to do before you do any machine learning. And so there's actually a lot of room for customization in Seaborn. So I'm putting. Yeah, let's look at this later. Let's go back. No, actually, let's look at it first. So here, this is the documentation for pair plot, and there's a bunch of options that you can use. And if you scroll down on the documentation page, maybe if I zoom in, you can see there's a bunch of different ways to plot various things, and there's a very good guide on how to do that here. And Seaborn not only does these pair plots, there's like a whole slew of other plots that you can use, that you can do directly on these databases or data frames. And as an example of this customization, here I'm just showing. Yeah, let me just run this, and I will tell you what it did to it, and we can go through these options that I set. Let me zoom out a little bit so we can have both the code and the plots on the same frame. Let me just scroll. Perfect. Here. Yeah. So now you can see. Now here there's a plot, or there's a field called hue, a keyword argument, and I said it color things according to species. So yeah, so one of the columns in our CSV file was species. So there's also a column in the data frame called species. So I told it to color by species, and I told it the diagonal kind is that here I call it KDE, which stands for kernel density estimate. So instead of a histogram, it's plotting these smooth KDE plots on the diagonal. And then also I said kind equals reg. So this is regression plots. And you can see there's now there's a regression plot for each of these different types of species for each pair correlation plot here. Yeah, so if we looked at this plot, for instance, we might see, oh, there's kind of a negative correlation here. But if we enhance the resolution to be for every type of species, you can actually see there's a positive correlation, but it's like 3 different positive correlations. Yeah, so this is also a very handy tool to look at your data. And finally, I'm just going to show you a thing called a heat map. So it's not so useful for this purpose, but what a heat map is basically, it's the just a graphical overview of the correlation coefficients between 2 sets of data. So for instance, the petal length and the sepal width, they have a pretty good correlation. And just like I noted before, there's kind of a small negative correlation between the petal width and the sepal width, because here we don't discriminate between the different types of flowers. So this is basically just a handy tool. If you have like things that don't correlate with your desired data, you can get an overview here. You might want to remove features from your data, or you might try to reduce noise on a certain part of your data or something. Okay, so I think this is like the turbo introduction to Seaborn and Pandas. So let's actually try and do some machine learning on this iris data set. So I'm not sure how many of you actually followed Guido's course yesterday, but yesterday he definitely talked about something called nearest neighbors and how you could calculate distances to nearby things. Yeah, but it's definitely, there is no requirement of having followed Guido's course today. So the type of machine learning that we're going to implement now is called K nearest neighbor, and it's a K and N for short sometimes. So it's a K nearest neighbor classifier for the iris data set. Let me just zoom in a little bit more here. And the way it works is you have your data set. So imagine these points here, the red and blue, are data points that we already have. And then somebody gives you the green point here and asks, well, how should I classify this? What type of data is this? Is this a red triangle or should this be a blue square? And what the k nearest neighbor does is look at the k nearest neighbors. So for example, for k equals 3, usually you only use odd numbers to avoid ties between classifications. So for n equals 3, for example, you would look at the 3 nearest neighbors, and that would be the red and the blue here. And then you would say, okay, this should be a red triangle. And the same thing if you had k equals 5, so the 5 nearest neighbor, you would take these 5, and you would count on the 3 blue squares and only 2 red triangles. So in that case, it must be a blue square that this should be. Okay, so this is basically how that works. And so to try and train our model and how to validate our model on this data set, we have to split it in 2 parts. So we need like a training part, and then that we can train our model so that we can use for all these points here. And then we also need a test part, so we can train our model on one part, and then we can calculate the accuracy on the other part. So this is what we call test and training data. I'm going to talk about this again tomorrow. So this is just what we need to know today. So we have to split our data set somehow. And I'm writing here training set, data to train your model, and test set data to evaluate or benchmark your model. And one thing that is important is that there's no overlap between the 2 data sets. So it wouldn't be good to train your model on some data and then also test it on the same data, because obviously if you trained your model on your data, it should be able to describe that data almost perfectly. But what you're really interested in is if somebody gives you some new data you've never seen before or the machine has never seen before, and then make predictions for that. So one way to do this, for this we're going to use something called scikit-learn, and I'm going to go back to scikit-learn a bit more. Scikit-learn is a Python. It's one of the official Python frameworks for machine learning. So I think every of my lectures I will use scikit-learn, and also it will be in all the exercises. So you're not going to have to know every scikit-learn piece of scikit-learn functionality, but I will guide you through it, and also I will give hints to what to use when and where. But yeah, let's start with splitting our data. So scikit-learn has a function called train test split, and it takes a Python or a pandas data frame, and then it splits it in 2, so a test set and a training set. So for example, one common way to split it is 70-30. You could also choose 50 and 20 or something. Doesn't matter. It depends on what your data is and what you want to use it for. And then you say test train split, and here is my pandas data frame. And then you say here in percent or as a decimal, really, what should my test size be? And then it splits back to also pandas data frames, just with smaller, or with the 70 and 30% split in this case. So let's try and run this cell here. Yeah, I guess nothing happened, or it doesn't print anything, but of course it does what it's supposed to do. So let's try and see what's in these 2 data frames. So let's run these train head. Whoops. Let me just click like that. Train head, and let's do this. Okay, so now you can see it. Basically, it took. Let me scroll up again. Here, so here it was like ordered 0, 1, 2, 3, 4, 5, 6, 7, and so on, and with all the various measurements and the species here. So what this train test split function does is it randomizes all your data, and it gives you 70%, in this case, random of your rows will be in the train, and 30% of your randomly chosen 30% will be in the test head, and it's also made such that they don't overlap. So this is a perfect way for us to divide our data here, and you can see the numbers are actually, they look random as they should be. There's no ordering or anything. Yeah. Okay. Okay, so one brief note about nomenclature. So here I'm using two words. I'm using a word features, and I'm using a word called labels. I apologize. Corona. So a feature is what we call our measurements that we use as input to predict something. So in this case, our features would be the petal length, petal width, sepal length, and sepal width here. And labels, that would be what we're trying to predict with our machine learning model. And so here I'm making two objects. So this is called train features and train labels. So the train features, there's a, yeah, let me just answer this question here. Can we fix the randomness with the seed function is a question from the chat. Yes, I don't remember exactly, but there's just like in NumPy, there's a way to set the seed. I'm not sure, I think it actually uses NumPy's seed function, but it's definitely possible because that's the only way to make a reproducible workflow. So this is for sure possible. But yeah, you have to look that up if you want to see, if you want to do that yourself. Okay, so I'm making two. Basically, I'm making two new. So these are actually also data frames, and this one called train features. Here I take train, which was the data frame I got out of my train test split up here. Let me zoom out a little bit so I can fit everything on the screen. And then I'm saying in brackets, just like with NumPy arrays, you can tell it what to take out of the original data frame. And here I'm giving a list of sepal length, sepal width, petal length, and petal width. So basically, this will now contain 4 numbers. So each row will be one number containing these, and our labels, so the things that we want to actually predict in the end, and train our model to predict. Here I'm telling it to give me the column name species. And the same for the features. Here I'm taking out, again, the features that we want to use for a machine. And the test labels, these are our species. So again, there'll be this column here, and up here it would be this column here. Okay, so I'm going to code the first steps to our simple classifier in NumPy, and then I'm going to switch to scikit-learn to actually do the training, because it's much easier to do this using scikit-learn. So I just told you that this is a k-nearest neighbor classifier, and to find out what a point belongs to, you have to calculate the distance to every point, and then you have to take the closest neighbors and then count those. So let's start here. So what I'm doing here is I want to query a particular point, and I'm going to do this all in NumPy. So I take the test features, so all the features, these numbers here for a test set, and just because I'm coding in NumPy, I use this NumPy as array to make this into a NumPy array, and I'm taking the 0th row. So I'm basically, I have a NumPy array that contains these 4 numbers now here. And for my training features, I'm just taking as array the training features. So this would be a matrix containing all these rows containing features here. And then I want to be able to calculate the distance between this point and then every point in this matrix, basically, or every row in this matrix. And yeah, we can use a function for that. So here I'm defining a function. I call it distance, and I'm implementing the L2 distance norm here. So the way I'm imagining it is you put in a row and another row, and this just calculates the difference between the rows. And then there's a function in NumPy called norm, So this is the L2 norm of that difference. So this will be the L2 distance between these 2 points, no matter how long these vectors are. And then finally, I return the distance. Okay, so now that I have my row, so this is essentially the green point in the figure I showed you before, and then I have all the red and blue, and I guess there's also a third option in this case as a matrix. And what I basically do is I say for I in range, and then I'm looping over every training feature I have, and then I'm calculating this function distance between my query, and then you can see I'm calculating to the ith training feature, and then I'm just printing the index and the distance. So let's try and run that. Oh, I forgot to run this here. Yeah, so now this is run. Now I can run this here, and you can see, yeah, it's basically, it has an index, and then there's a bunch of distances. And if we wanted to classify it, we could search for the, for example, if we do k equals 5, we could search for the 5 nearest, and we could look up in the data frame whatever the thing with that index has for type, and we could find out what it was. Now this would be a lot of coding, so let's actually try and do this instead of implementing everything ourselves, because that's usually not how we want to go about doing things in your day-to-day life. You actually want to use as much code that is made by others as possible. And especially for machine learning, there's a lot of really advanced machine learning procedures that you can use. And one of the implementations of this is in this toolkit called scikit-learn, and it has I think it has 15 different classifiers and 20 different forms of regression, and it just has so much. There's so many things you can do in this. And here in the lecture slide, there's a link to the documentation, and you can basically find every type of machine learning in scikit-learn. Okay, so now let's see how to do this training in scikit-learn and how to do the prediction. And the first thing we have to do is we have to find the right classifier, and you can just go here to this link, and there's actually a code example of how to do it. And the one we were interested in, I looked this up beforehand. It's called k-neighbors classifier, and then after you import it, you can initialize an object, and it has a hybrid parameter called n neighbors. So for instance, if we want to do the nearest 5 neighbors, we write 5, or the nearest 3 neighbors. For this demonstration, I'm using 15 for no particular reason, really. We could have used any number we could have, and we could even have optimized this number. Maybe it works better with certain numbers than others. So optimization of numbers like this, we call these numbers hybrid parameters. I'm going to talk about that tomorrow in the class tomorrow. But for now, let's just use 15 just because it's convenient, or yeah, not really for any particular reason other than I just chose 15 when I wrote this code here. So the next thing you do after you initialize your object is that your classifier object here will have a method called fit. And the only thing you have to do is you have to give it 2 arguments. So you're training features and you're training labels. And these features, they can either be a pandas data frame, and the same with the labels can also just be a pandas data frame, or they can be simply a numpy array or lists of numbers. So it works pretty well. Scikit-learn is pretty flexible with what you can give it as input here. So now we actually trained our first machine learning model, and it prints some output just with all the parameters that you're setting implicitly. So there's actually a bunch more parameters here. You can see that if you mouse over, I can't actually point to them, and you can read about what they do in the documentation. For I think the most important for ours is n neighbors, and then there's this metric which is called the Minkowski metric. And that's how you calculate the distance. And the Minkowski distance with p equals 2 is just the L2 norm. So just the norm of the difference between 2 points here. And also weights equals uniform. So there's no, you can put higher weight to certain data points to weight those more. But yeah, take a look at the documentation down here if you want to like tinker with these numbers yourself. And if you want to try and see like how you can make a better classifier maybe out of this. Okay, so now we actually trained a model, and now we're ready to predict models or predict new labels. So we can take the features from the test set. So that would be what we have here. So we take the features here, this feature, and so on. And then we're going to ask the machine what is the species that come out here. So it's just going to calculate which are the nearest neighbors, and it's going to predict or print or return the predicted labels. And then what I'm doing here is I'm printing the predicted labels afterwards. So let's run this cell here. Boom. And now it's just saying setosa, versicolor, setosa, versicolor, setosa, versicolor. And that looks very much like we have here, setosa, versicolor, setosa, versicolor, setosa. So that's a good sign. Well, it seems like it actually learned something. Let me just do like this. So of course, you also want to be able to benchmark your model. So you need some kind of metric, how good, like to tell you how good your model is. Scikit-learn also has something called scikit-learn metrics. And so you can actually, if you look up scikit-learn metrics, there's like I don't know, maybe 100 different ways to calculate metrics for your machine learning model. So one of them, the ones I'm interested in here is the accuracy score. And the accuracy score just tells you how many correct and how many incorrect data points you have. And it makes that into a number, in a decimal number. And what I'm giving this accuracy score, which I'm importing from this metrics module, is I'm taking the predicted labels. So this list here that just came out of our classifier, and then I'm taking the test labels. So the labels that we got all the way back here. So the test labels are the true or the correct answer for the test set. So the part of the data set that we did not train our model on. So that's what we're interested in using. So let's run this and see how accurate our KNN classifier is. And it says 97.8%. So that seems pretty good to me, at least. I'm convinced that this works. So another question is, I keep doing this. What if we want to use another classifier? So they literally all have the same syntax and they work the same way. So for example, if we wanted to use a nearest centroid classifier, we can import nearest centroid from scikit-learn neighbors. And then we could make a new classifier like this. And the nearest centroid, instead of counting how close all neighbors are, it counts or it calculates the centroid. So the mean average of all the features for a given class, and then it calls that the centroid, and then it classifies a query point as just the same as the nearest centroid. So let's say we wanted to use this, so I can mark this and press Control-C. We can basically, let's do it like this. We can put it in here. We can just uncomment this. Actually, let's do this slightly different. So just to show you how similar the syntax is for other types of machine learning. So instead of importing k-neighbors classifier, we import nearest centroid, and we can just comment this out. And the same way for instead of initializing this object called classifier from this class, let's comment that out. We do a nearest centroid. And now you can see it prints out that we're using the Euclidean metric, and I am not sure what this shrink threshold is. And then again, we run this, and now it's actually, because we ran this fit method, it has actually trained the model. And now we can use this trained model to predict again. and we get some values out, and then we can run this cell here, and we can see what the accuracy score. And apparently, they give the same accuracy score. So that was easy to change machine learning method. I hope you're convinced of that. Okay, let me know. So the next part is about linear least squares regression. So let me know if there's if there are any questions to what we've been doing so far. Just write your questions in the chat. Otherwise, I'll go on and talk about linear least squares regression. So this is what you will be using in the exercises, and it's probably the simplest form of machine learning there is, like period. Yeah, it doesn't look like there are any questions, so I'm just going to go on. So let's imagine we have some data for a linear function. We have y, and it's equal to 1.2 times x, and then we have some numerical noise here. So what I'm doing here is I'm just generating some of that data. So I have np.a range. So these are the x values we have. And then I'm creating some y values. So I'm multiplying x by 1.2, and I'm adding some normally distributed data to that. And you can see I print x and y. So we have 100 of each type of points. So let's do our little exploratory data analysis in this. I'm just going to plot the data really here. And you can see our x values and our y values. And then here, this is like the true, the green line is the truth. So that's x times 1.5 or 1.2. And the blue are the numbers that we will be using for our training data here. Okay, so what is linear regression? So linear regression, it approximates a function as a linear function. So for instance, y of this vector x, so it's x1 multiplied by some weight a1, or some coefficient a1 or alpha 1, and then x2, so the second entry in this vector, multiplied by some regression coefficient a2, blah, 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 up to xn, multiplied by alpha n. We can also write this in vector notation. So y of x equals x dot product with alpha. So I'm terribly sorry, but for some reason, this should have been a bold alpha to show that it is a vector, but that doesn't render in Google Colab currently. So please bear with me. If I just say alpha, I mean that is a vector here, just like bold x is also a vector. And x, that's the vector or descriptor or representation for a data point. So for instance, in this this flowers data set, x would be here, it would be like this vector here of these 4 numbers. So fitting your model or training your machine, training your machine is, that's what you do when you find the best set of alpha values here. And so let's say we have a lot of y values and we have a lot of x, these feature vectors or x values. We can write this equation like this. So this is a column vector that contains all our y values, and this is a matrix where all the rows are the features. And then this alpha is, that's a vector with all our regression coefficients. And what you do then is that you minimize the least squares so that you minimize the error, so argmin. So you take all your reference values of y, and then you subtract this product. So you basically, your error is if you subtract the right side from the left. So you just move this over, and that's what you call your residual. And you square this, and you find the best set of alphas. So those of you who took Guido's course the past 4 workdays, you should be expert in doing this. But I'm just gonna go through how to do it in NumPy real quick. And basically, there's a way you can solve this analytically called, yeah, there are many ways, but one of them is built into NumPy and is specifically this function called NumPy linear least squares. So just a quick hack that we have to do here is because we're expecting to have a matrix here, but our x values is just like one long list. So I'm just reshaping it to a matrix that is it has 100 rows, and every row has one entry. So this is it's like 100 by 1 matrix. This is just something I have to do to format into this least square. And so the least square, basically you put in your x and your y values, and then it returns the best alphas here. So I put in my x values and y values, and it returns the alphas and also the fitting residual and the rank of the problem. And it uses something called a singular value decomposition. So it also returns the singular values if you're really into looking at deeper into how the fit went. But we don't need to look into all these right now. We just wanted to run and give us the alpha coefficient. So let's run this cell again. So ignore this. Google Colab uses I think it uses an older version of IPython, which sorry, not of IPython, of NumPy, which has it gives a warning about arcont. So you will also see this in the exercises. And please just ignore this arcont future warning. The number that we're interested in is the alpha number, and you can see here it comes out as 1. Roughly 2 here, 1.199 something, which of course looks suspiciously close to this 1.2 that we're using to generate our training data. So this is basically how we can interpret our 1D function here via this alpha coefficients. Yeah, so here this is our fitted function. And of course, we have our original function here, relationship that we're interested in, and we found 1.199. So that's pretty close to what we were looking for, right? Okay, so let's try and do some predictions here. So I'm making some random test values, and what I'm doing is I'm just using this function called numpy.random.random. And just to make sure that it fits into this formula here, I want it as a matrix that has 15 rows of each one item. And numpy.random.random gives us numbers back from 0 to 1. So I'm just multiply it by 20 here. So we get, so here we have from 0 to 20. So I'm just multiplying by 20 to scale up. So we have random numbers in this entire range here. So let's run this. And here we get some random numbers between 0 and 20, just like we used to. And then, yeah, we basically use this formula again. So we have our test x's, and we have the alpha coefficient that we fitted here. So if we multiply those, like using the matrix multiplication tools in NumPy, for example, we'll get a vector that corresponds to the y values for the test points. Yeah, so here I'm multiplying x test by alpha using np.metmul. And then what I'm plotting here is just I'm plotting the true relationship, and I'm plotting the training data and the test data. And I'm also adding a legend to the figure. So let's run this and see how the fit went. And now you can see we actually fitted. Yeah, so the green curve is the true relationship. So y equals x times 1.2, and the blue are the training points. And it seems like, and the red are the random test points for which we didn't know the values before. And so it seems like we actually were able to regress these properly. So yeah, it seems like we were able to do linear regression using NumPy pretty easily. Yeah, are there any questions to linear regression? Yeah, let me know in the chat. So basically the exercises for today, which I will introduce next. No, they don't see. Okay, so the exercises is data set. Yeah, let me just, maybe I should open it and I can show it to you. Maybe that's better. So open notebook and go to GitHub. And we go to Python intro here. And we have machine learning exercises 1 here. Stand page or leaf page. So I'm just going to give you a quick introduction to the exercises for today. So I would recommend that you have them done before the lecture tomorrow at 2. Yeah, I'll upload the solution to them maybe right after the lecture or something tomorrow as well. But basically what you're going to do here is you're going to do a linear least squares regression yourselves. And basically here you will be taking all the way from a data file, a txt file, to a regression model. Yeah, and the first, maybe I'm going to show you how to just do the first couple of steps before we begin the exercise. So the first point is here, I uploaded again some txt files that contains features and the prices. So basically the features and the labels, as we call them, or the representations or in the labels for our data. And you download them using basically this wget command again. So just click here, run anyway. So now there are you can see the text files are saved, Boston features and Boston prices saved. You can also, instead of, so this, this exercise, because I kind of want you to like understand how to do linear regression and how it works, we're going to implement most of it in NumPy instead of this pandas tool I just told you about at first. And then later in the exercise, you will use scikit-learn to implement this. So you can also load a text file into a NumPy array, and you do it using this np.load txt. So let's just run this like that. And then we can print the shape, because these are now NumPy arrays. So they have this property called shape. So for instance, the features, you can see this is a matrix with 506 rows and 13 entries, 13 columns in each row. So basically we have 506 houses, and each has 13 observations, and also the prices, there are 506 prices. And we can print them. And you can see the prices, these are in thousands of dollars. And our features for each house is just like a matrix of numbers. Here is like a legend of what the index in the feature matrix, the columns, the various columns in the feature matrix does, and then the description of what that is. And basically your task for this set of exercise is to go through all the steps that we looked at today. Let me zoom out a little bit so we can see more. So the first exercise is do some kind of exploratory data analysis. So like do something where you plot the data. Then you have to split the data in like train and test sets, just like we did in the exercise. And then the next part is coding this regression fit. So using this least squares yourself. And then you can make some predictions in questions in exercise 1.4. And then in 1.5, I have instructions on how to do all the steps with very few lines in scikit-learn. So hopefully, once you've done these exercises, you'll be able to like say that you've implemented linear regression yourself, and you also know how to implement it in scikit-learn. So you could basically drop in other forms of regressions in this code. So this will be a very good code to have for future research purposes for yourself also. So I really recommend that you go through all of these steps and also do exercise 1.5 because this is really the way that you're gonna use machine learning, I think, for most of you. Yeah. So this is all I had for today, I think. So let me know if there are any questions. Otherwise, I think we will end the lecture here. Yeah, and tomorrow I'll be giving you the graded exam for this course. So If there are no questions, I'm going to end the lecture here, and I want to say thank you for listening for today. Yep. It doesn't seem to be any questions. So I will see you tomorrow at the same time, same channel. Bye.